I'll go into some of quickly the carbonation test. So you take a core, remove the core, and then spray a phenolphthalein solution. So if the pH of the concrete sample is more than about 10, 11 and all that, it will turn pink. If the pH is less, then you will get a colorless surface. So this is a plaster and this is a concrete. So much of carbon dioxide has gone diffused into the concrete. So what happens, I mean, I don't want to go into concrete technology, and the moment carbon dioxide diffuses in, it reacts with the calcium hydroxide, converts it to calcium carbonate. So it is the calcium hydroxide which supplies pH. When the pH comes down, naturally the depassivation happens. So the moment they put the phenolphthalein solution, if the pH value is high, then it will pink. If the pH value is low, then it becomes colorless. So why we are doing this is, we are not doing all these tests for fun. We are doing it for a rehabilitation methodology. So now we have to tell that you have to chip open all the carbonated concrete. So here it comes into play. So this much concrete has got carbonated. When you are giving a rehabilitation methodology using microconcrete jacketing, chip open till the carbonated concrete, and then then you have to go with the microconcrete. Half-cell potential test. I'm not a great fan of this test. So you use a multimeter, copper sulfate thing, then expose the rebar, and then wet the surface, and you have to wet the surface properly. And then you get some numbers like -350 or -450 or something. And ASTM gives you a certain thing. More negative than -350 is 90% probability of corrosion. Between -200 to -350 is uncertain. And then more positive than -200 millivolt, there is no possibility of corrosion happening. Why I'm not a great fan of this is, many of the structures, whether it's a marine structure or a bridge structure or any structure we go, the standard scope for me is to assess the condition of the concrete. Based on the condition of the concrete, give a rehabilitation methodology along with the bill of quantity. The bill of quantity should be perfect. No, it should be encompassing everything. What I have tested, what I have not tested. So when most of the structures we go, you find the concrete has spalled, rebar has corroded, has gone 30% loss in diameter. So there is no point in going and doing a half-cell potential test on those areas that have already got corroded. Anyway, I'm going to go take them for rehabilitation methodology, and I'm going to calculate the bill of quantity. But what about the areas which look nice, which look visually good? So generally, I focus more my half-cell potential test on those locations which are visibly good. So I chip open and then do a half-cell potential test on those locations, so that I am very sure that when I prepare my bill of quantity, I don't have to include those areas. Because anyway, the areas what you see, you are going to take into your bill of quantity. But then the areas they're looking very nice, you have to be very sure that they are not going to go for corrosion in another 2 years or 1 year down the line, where the depassivation already taken place. So we generally, when I do 10 locations, we do about 7 locations on the visually good locations, and then 3 on the distress location, just for comparison purpose, because my scope would be mostly towards giving a rehabilitation methodology and the preparation of the bill of quantity. And then I give the bill of quantity only for the visually corroded locations. There is no point in going in and even doing an investigation, because we have to be very sure about the locations which are looking good, but which may be getting into, maybe in the process of getting corroded. So this is how I use the half-cell potential test. And the chloride, we take a drilling machine, drill the powder sample, that is IS code. You can find out the acid-soluble chloride, and then you can do a pH also, you can do sulfates also. In this, what we do is we drill 0 to 20 mm or 0 to 20 mm, then 20 to 30 mm, 30 to 40 mm, and then try to find the profile, to what depth the chloride has gone in. Slightly approximate. I'd be more happy if I take a core and then put it in a lathe, and then using a tool, I precisely cut the 0 to 20, 20 to 30, because in a lathe, it is much easier. For example, IIT Madras has that facility. Because we are more into consulting, we don't have that facility. So when I drill through the powder sample, even though I drill from 0 to 20, take the sample, and then I use a blower and knock it off, and then I go 20 to 30 mm, there is every possibility something may get jingled up, like jungled up, and then I may not get a true profile. So if you take a core and then put it in a lathe, and then with a tool you precisely cut it, then you do it. Testing is fine, but then taking a sample and you want a very precise chloride diffusion through the depth of the cover concrete, then you may have to go for that kind of a core test, and then put it in a lathe and then measure the thing. So IS code again is very sketchy. 456, it says the maximum acid soluble chloride should not exceed 0.6 kg per meter cube, but they say it should be at the time of placing of the concrete. They are not sure about what should be the threshold number 10 years down the line, 20 years down the line. But anyway, it's okay. It gives you some idea. And most of the marine structures we do, it's about 2.5 kg, 3 kg per cubic meter. And when it is pre-stressed concrete, it's 0.4 kg per meter cube. So